Okay, this is Chapter 3, Control Volume Analysis, Part 7. In this video, I'm going to do the derivation of the famous Bernoulli equation. As you will see, Bernoulli equation is a powerful tool in fluid dynamics, but it's limited to steady, incompressible, and frictionless flow. We'll talk more about the limitations as this video proceeds. The Bernoulli equation is named after Daniel Bernoulli, who lived in the 1700s. And it should also be mentioned that a substantial amount of sort of refinement of Bernoulli's equation was done by Euler, a Swiss mathematician that lived in the similar time period. So we're going to derive Bernoulli's equation, talk about its limitations, and then I'm going to do a simple numerical example, which is flow discharging from an open tank. That's probably the simplest example, just to talk about how you use Bernoulli's equation. And then I'm going to do a few more videos that talk about some of the more interesting and practical applications of Bernoulli equation. It's particularly important for flow rate measurement, for making flow measurements. Okay, moving on to the derivation of Bernoulli's equation. Let's talk a little bit about the assumptions, or in other words, the restrictions to this equation, and I'll come back to this in more detail because it's very important not to misapply Bernoulli equation. So the assumptions are the flow is steady, so we don't have any transients. We're also assuming that the flow is incompressible, so in other words, the density is constant. We're also going to assume that the flow is along a streamline. So Bernoulli's equation applies to flow along a streamline, as you'll see as we move along in the derivation. So remember what a streamline is? I've drawn here over on the right-hand side a number of streamlines. And remember, streamlines are lines drawn through the flow field such that the streamlines are always tangent to the velocity vector. So no flow crosses a streamline. If you don't recall this, you might want to go back and have a look at the video for Chapter 3, Part 1, where we talked about flow visualization and streamlines. The other sort of assumption in the derivation of Bernoulli's equation, and this is a very important one, is that the flow is frictionless. So it really only applies to fluids that have no viscosity. So it really applies to so-called inviscid flow. And the word inviscid refers to a fluid that has no viscosity. Now, all real fluids, and fluids in the real world, have viscosity. So the application of Bernoulli's equation is really restricted to regions of those flows, of real world flows, that are nearly frictionless. And we'll talk about that towards the end of the video. So there'll be a detailed discussion of the limitations of Bernoulli's equation following the derivation. So let's move on to the derivation. So what we're considering here is flow along a streamline. And over on the right-hand side, I've drawn a little fluid particle. So a little mass of fluid, incremental or differential mass of fluid that we're going to follow along as it flows along a streamline. And S is the local streamline direction here. And remember, we're considering a steady flow, and the fluid particle has volume V. In fact, it has length ds, cross-sectional area dA, so the volume would just be dA ds. But I'm just going to use the symbol here, V with a line through it, to distinguish that from velocity. So that's our incremental volume, and so our incremental mass of our little particle that we're tracking is rho dV. So now we can apply Newton's second law for this system. We're not doing a control volume analysis this time. I should mention that the derivation that I'm going to do here is a more classical derivation than you'll find in most textbooks. The textbook that you have does it using control volume analysis. This is a more classical approach by following a particle or in other words, a fixed mass along a streamline. So we're using a system approach here, and the system is a fluid particle of mass dm. So we can apply Newton's second law just directly here, that the sum of the forces on that little fluid particle equals mass times acceleration. Of course, it's a differential or element, so it's dm times as, where as is the acceleration in the streamline direction, so the local streamline direction. I've made the little substitution here that dm equals rho dv, and for acceleration I've just expressed it as dv dt. Now you might wonder, and we'll stop here for a moment and just talk about this, how can the term dv dt exist in a steady flow? Because in a steady flow, you wouldn't expect any changes with time. I'll let you think about that for a moment. Well, the answer is that the reason dv dt can exist in a steady flow is because what we're following is we're following a particle along a streamline. And as that particle moves along the streamline, it can, even in a steady flow, it can move from a low velocity region to a high velocity region. So the particle moving through the flow experiences a rate of change of velocity with time. Let me just go back to the previous slide just to reinforce that point. So remember these pink lines here are streamlines, and no flow can cross a streamline. So we have the same amount of flow coming in here as going out here, right? So the flow must decelerate, right? You've got the same amount of flow passing between these two streamlines as passing between these two streamlines. So the velocity here must be substantially higher. So the flow decelerates as it moves from left to right. So if you were following a fluid particle along the streamline, it would experience velocity changes in time, even in a steady flow. A steady flow really refers to the fact that at a point in the flow, at a fixed x, y, z location in the flow, the velocity doesn't change. But as a particle moves through that flow, it can experience velocity changes in time. So I hope that's clear. Let's go back. Okay, so now we've convinced ourselves that dv dt can exist in a steady flow when you're tracking a particle that moves along a streamline. So now I'm just going to do a few little tricks to basically get our differential equation. So I'm going to apply the chain rule to Newton's second law. I'm going to change dv dt here into ds dt ds dt di v di s. So you can see if you were to cross those out, you'd end up with dv dt. So just a standard chain rule. Oh, and I've applied partial derivatives here to the v term because in a two-dimensional field, velocity would be a function of x and y. So it's a field variable. Now, we note that this term ds dt, the rate of change of distance with time, is just the local velocity. So that's just v here. So we can rewrite Newton's second law as, of course, rho dv, that's dm, and then v dv ds. One more little trick to do before we move on. What I'm going to do is I want to bring this velocity inside the derivative, and if we do that, we get 1/2 di by ds of v squared. Now, if you can prove that this is equivalent by just evaluating this derivative, right? If you evaluate this derivative, you're going to get 2v dv, and that's going to cancel out the half, and you'll recover the expression over on this side. So that's just a little trick, and now you can see that if you look at this term, it looks like kinetic energy, right? This is mass, and this is 1/2 v squared. and then there's a rate of change with distance, right? So it's actually the rate of change of kinetic energy along the streamline equals the sum of the forces on the fluid particle. So that's another way of expressing Newton's second law. So I'm going to call that equation 1. So we've rewritten Newton's second law in a form that is going to be useful for our streamline analysis. Okay, so now we're going to consider the forces on the particle. We've dealt with the rearranging F equals ma. Now we need to get the sum of the forces. So I've drawn over here on the right the particle, and this is a bit of a complicated diagram. There's the particle in blue, and we have the weight force, the differential weight force dW, which is just dm times g. Remember, dm is rho dV, density times volume. So there's our incremental weight force that acts downward. We're assuming here that we have gravity acting downwards. There's also pressure forces. Remember, this little blue fluid element has a cross-sectional area dA, so there's a pressure force pdA and another pressure force on this end acting in the opposite direction. And here's the really important point, is there's assumed to be no viscous shear stress. So tau that would act on the sides of the fluid element and it would oppose fluid motion is neglected. And why is there no tau? Well, because Bernoulli's equation, we make the assumption of frictionless flow. So tau equals 0. You'll find no terms in Bernoulli's equation contain viscosity for that reason. And that limits the application of Bernoulli's equation, and we'll talk about the implications of the frictionless flow assumption later on in this video. So for now, given that we've neglected viscosity, we can now sum the forces that we have, which are weight and pressure. So the sum of the forces in the S direction, remember S is in the streamline direction here, S, is PdA, that's the pressure on the bottom side of the element, that acts in the positive S direction. And then I've done a little Taylor series here, that the pressure at the other end of the element moving a little distance ds along the fluid particle is P plus dP ds ds. And notice the partial here, because pressure, of course, is a field variable. In a two-dimensional field, it would vary as a function of x and y, and we're just taking the derivative in the s direction. And then multiplied by dA, of course. So there's the pressure on the other element, other end of the fluid element, and it acts in the negative s direction, so you have a negative sign. And then gravity, or the weight force, the incremental weight force dW, we need to take the component of dW that acts in the s direction. Of course, it acts in the negative s direction, and so that becomes, and that's where the sine theta. So this is this term here is dW, the differential weight, and then times sine theta, so we get the component in the negative x direction. Now we can simplify this. PdA here, and we have minus PdA, so that term cancels with that term. And so we're just left with minus dP ds dA, and then minus rho dV g sine theta. So here's the simplified equation here. Now, I've drawn the streamline over on the right-hand side in the bottom. I've drawn the streamline here, and I've defined, notice I've defined this angle, theta. As the flow travels uphill, as it travels to higher altitude, it gains potential energy. So we need to take into account this altitude z. And we can do this with a little bit of standard trigonometry, right? So if we think of this triangle here, sine of theta is opposite over hypotenuse, so sine theta equals dz over ds. So simple trigonometry, sine theta equals dz ds. So I'm going to substitute that in for sine theta. Also, I noticed that ds dA here, remember, ds times the cross-sectional area of the element will give you the volume. So I'm going to make the substitution that ds dA is just the incremental volume. So I'm going to simplify it further, and our equation becomes sum of the forces equals minus di P di S times the incremental volume, rho, the incremental volume G, and then dz ds. So I'm going to call that equation 2. So now, in the next slide, I summarize this, I think. We have equation 1, which is Newton's second law, where I've rewritten the sort of mass times acceleration term in terms of the streamline direction S. And I've done a few other manipulations as well. And then I've summed, in the previous slide, we summed the particles on the fluid. And we've got the pressure force and the gravity force. No viscous force, because we're assuming that this is a frictionless flow. The fluid has no viscosity. And so that's where it comes in. That's where that assumption comes in. So now we can equate these two. We can set that equal to that. And that's what I've done. I've equated the right-hand sides of equation 1 and equation 2. So you'll see that's what we have right here. Now you can see right away that each term has this incremental or differential volume. We can get rid of that. Oh, in addition, we have di by di s, di v squared by di s, di p by di s, and dz by ds. It's not a, this is a full derivative already. Now, since the only independent variable is s, we can convert the partial derivatives into full derivatives. When something's a function of only one variable, you can have a full derivative. And in addition, I can see going from this equation to the next one, it looks like I've divided by rho as well. So a little bit of simplifications here. So that's all I've done there. So there's the kinetic energy term, there's the pressure term with a 1 over rho, and the density's gone here. Oh, and I brought these over to the side so the signs are positive. So that, to me, that looks correct. Now, this applies along a streamline. And if you consider incremental distance ds, you can actually drop the ds on the bottom. And so if you actually restrict yourself to being on the same streamline, you can just say 1/2 dv squared plus 1 over rho times the incremental change in pressure, differential change in pressure, plus g times the differential change in z equals 0. So I've dropped, when I've made the restriction that I'm on a streamline, I've dropped the ds. So now we're just applying these differentials along the same streamline. And so I've rewritten our equation from the previous slide here. Now you can integrate this equation along the streamline. So I've just written each one of the terms with an integral sign in front of it. And of course, the integral becomes the integral of 1/2 dv squared just becomes v squared upon 2. 1/2 can come outside of the integral. We're assuming constant density. So again, 1 over rho is a constant, so this becomes dp upon rho. And g is, of course, a constant, so it just becomes z, and that equals a constant. So I'm doing the indefinite integral version of this, and you should keep in mind that the assumption that we made was that to get rid of the ds was that this equation applies along a streamline. And so the result is for flow along a streamline. We'll talk about the meaning of these terms in a minute. This is the famous Bernoulli equation. Another way to integrate the equation is to perform the integration between two arbitrary points along a streamline. And here I've drawn a streamline, and at point 1 we have pressure 1, elevation 1, and velocity v1. And then as we move along the streamline to some other arbitrary point p2, or point 2, we have pressure p2, elevation z2, and velocity v2. So we can perform this integration from specific points on the streamline. And so our integration, we have a definite integral with the limits. So we have a limit from v1 to v2, the limit from p1 to p2, and the limit from z1 to z2 on the potential energy term. And so when we perform this integration, we get 1/2 v2 squared minus v1 squared, p2 upon rho minus p1 upon rho, and then gz2 minus gz1. And you can bring all of the terms involving point 1 over to the left-hand side, and all of the terms involving point 2 over to the right-hand side, and you get this equation. This is an alternate form of the Bernoulli equation. This is the form that we will most frequently use. When we do problems, you'll see it's most convenient to apply Bernoulli's equation from one point to another. And again, you should keep in mind from this derivation that this equation applies on a streamline. Now I'd like to talk about the physical interpretation of the Bernoulli equation. You've probably started to spot some things in the equations like kinetic energy and potential energy. Well, Bernoulli's equation can be interpreted as an energy balance. Remember, this is an idealized frictionless flow, so there's no energy loss caused by viscous dissipation. Viscosity normally, sort of like friction, burns up energy in the flow, but we're neglecting that. So the total energy of the flow remains constant. And there's 3 types of energy in the flow at any given point. The first term here is the kinetic energy, and of course, kinetic energy is 1/2 mv squared, so this is per unit mass. This is something called flow work. Some people call it pressure energy or pressure work. So it's the energy associated with the pressure. And this is potential energy. Remember, potential energy from your physics course is weight through a height. So this is potential energy per unit mass. And the previous term, of course, is pressure energy per unit mass. So when you add these 3 terms up, you get the total energy per unit mass of 0.1. And this is a conservative system. There's no energy being dissipated by viscosity, by friction. So that equals the total energy at 0.2. So at 0.2, we have some kinetic energy per unit mass, some pressure energy per unit mass, and some potential energy per unit mass. And so if the flow speeds up and it gains kinetic energy, that must have come at the expense of either pressure or elevation. Elevation must have gone down or pressure must have gone down. And we'll talk about that more in subsequent examples. If we divide the Bernoulli equation by g, gravity, we get another form, this form here. And in this form, if you look at it, you can see because our potential energy term just becomes Z. And this equation is dimensionally homogeneous. So if you check it out, you'll see that this term here, the pressure term, the pressure energy term, and the kinetic energy term also have units of meters. Oh, and in this equation, because we've divided by g, this term here is rho g, which is the specific weight. And you saw specific weight in chapter 1. It's a property. It's the weight of fluid per unit volume, newtons per cubic meter, or pounds per cubic foot. So all the terms have units of distance, height, in meters or feet. And in fluid mechanics, this is called head. And so the slide's entitled The Fluid Mechanics Definition of Head. And indeed, each one of these terms has its own little name. The kinetic energy term here is called the velocity head. The pressure or flow work term is called pressure head. And Z, of course, is just elevation head or just head. And it's important that you get familiar with this sort of nomenclature because it's widely used in the fluid mechanics, fluid dynamics industry. And I'll show you on the next slide. If you just go to the web and you try to purchase a pump, for example, it'll assume that you know what head is. And I just Googled pump specs and I came up with this, a company called Liberty Pumps that makes submersible pumps. And here's 3 different submersible pumps. They're different models. They make a 1/3, half horsepower, half horsepower, and 3/4 horsepower submersible pump. You may have had one of these. I remember a friend of mine when I was a teenager, they had a bit of a leaky basement, so they had a sump pump, submersible sump pump, and when water would flow into this little low section well in their basement, it would pump out, and you'd hear the sump pump clicking on to keep the basement dry. So that's a typical application. But if you want to buy one of those, you end up with a specification chart shown over here on the right. So this is total head in feet, or total head in meters over here. And this is the pump discharge rate, so the amount of volume per minute in gallons per minute that the pump can pump, or at the top here I noticed they have it in liters per minute. And so it's kind of interesting if you look at this. What this is telling you is if this pump were pumping through a horizontal pipe, so no change in elevation, if it was a short horizontal pipe, you could get about the smallest pump, this 1/3 horsepower pump here, would pump about, in a short horizontal pipe, full out, it would pump about 50 gallons a minute. But if the pipe changed elevation, as you pump to higher and higher elevations, if you can pump to what that looks like about 22.5 feet maybe, and at 22.5 feet, you don't get any flow. So as you pump to higher and higher elevations, you get less and less flow from the pump because it's having to put the energy of the pump into raising the fluid. And that's typically how it works. We'll talk more about pumps. That's just a little introduction to the concept of head in fluid mechanics. Okay, I promised I'd talk more about the limitations on the use of Bernoulli equation. We're going to use it widely in this course, but it can be easily misused, and so I want to talk about that a little bit. The first requirement is that you have a steady flow, and most of the flows that we're going to consider in this course are steady. It can also be applied for flows that are changing slowly. And in fact, the example I'm going to do of an emptying tank is a situation where it's not really a steady flow, but it's a very, very slow transient. The other assumption, and you saw when we performed the integration, we assumed the density was a constant in the integration, so we're assuming incompressible flow. So Bernoulli's equation is great for liquids, but you have to use it with some caution for gas flows. Gas flows where compressibility effects are small, you can use Bernoulli's equation. Remember from, I think it was chapter 1, we talked about the idea of compressibility effects and this idea of the Mach number. The Mach number being the speed of the fluid over the speed of sound in the fluid. And just to illustrate here for room temperature, and I've used the sort of chapter 1 calculation, we're talking about velocities less than 0.3 of the speed of sound, c. The speed of sound is square root of kRt. K is the ratio of Cp to Cv. I apologize to the biomedical engineering students who have not taken a lot of thermodynamics. That may not be such a familiar term. R is the gas constant for air, 287 joules per kilogram K, and T is the absolute temperature. And I've taken it roughly 300 K. And you evaluate this, what this is saying is that you can use Bernoulli's equation for air at room temperature up to pretty high velocities, up to about 100 meters per second. which is around 370 kilometers an hour. So you're okay for most gas flows, but not high-speed gas flows. The other assumption that you're probably more concerned about is this idea of frictionless flow. Bernoulli's equation was derived neglecting the shear stress on that fluid element. There's no viscous term in the Bernoulli equation. So Bernoulli's equation does not apply near solid walls where viscous effects dominate. And right at the solid wall, viscosity causes the fluid to come to a complete halt. It's called the no-slip condition. We talked about it in chapter 1. So you certainly can't apply Bernoulli's equation at the wall, or really anywhere near the wall. It also doesn't apply in regions of intense mixing, where you have a lot of energy loss caused by turbulence in the flow. So if you throttle a flow across a valve, and by throttling I mean you drop the pressure by maybe partially closing a valve, you won't be able to apply Bernoulli's equation across the valve because there's energy in the flow is not constant. There's energy losses. We'll talk about how to account for those later in this chapter, but when you're using Bernoulli's equation, you can't apply it across a throttled valve. As you saw, the derivation also made the assumption of flow along a streamline, and in some cases, you might have different constants for different streamlines. So you'll see in the example I do, I always draw a streamline to remind myself that I have to apply Bernoulli's equation along a streamline. In addition, we saw that the total energy in the flow at 1 equals the total energy in the flow at 2. So we can't be adding energy or taking energy away from the flow between 1 and 2. So number 5 here says no mechanical devices. You can't have any pumps or turbines between the 2 points on the streamline where we're applying Bernoulli's equation. We can't have any addition or extraction of heat or work in that region since the energy is constant along the streamline. There are some exceptions to this. You would be normally applying Bernoulli's equation to isothermal flows. No pumps and no turbines. Again, later in this chapter, we'll relax that assumption. I'll show you how to analyze systems that have pumps and turbines and losses due to valves, which is what practical engineering problems usually involve. But for now, when you're using Bernoulli's equation, we can't deal with those issues. This figure is taken from your book, talking about the limitations on the use of the Bernoulli equation. And they make some of the same points that I've already made. If you're looking, they're showing here a jet, the one on the left here, they're showing a jet aircraft in a wind tunnel. And what they're saying is you can apply Bernoulli's equation away from the wall. So it's valid away from the wall, but very close to the wall of or the surface of the wind tunnel or the surface of the aircraft. Viscosity dominates and you have the no-slip condition. And so you shouldn't be applying Bernoulli's equation very close to the surface. Now, in reality, the viscous boundary layers, that's what these are called. This is called a boundary layer here, where the flow is slowed down by the action of viscosity, are much thinner than what are shown here. They're typically of the order of about 1 centimeter. Of course, it depends on the Reynolds number. The higher the Reynolds number, the thinner the boundary layer. You'll learn more about that as we go on. So the sketches are shown here just as sketches. Really, you have to get quite close to the wall within about 1 centimeter before Bernoulli's equation breaks down. Okay, in B, they make the point that I made also, that you can't be adding work between points 1 and 2. So if you were analyzing a streamline here from point 1 to point 2 over here, you've got work addition by this fan, right? So Bernoulli's equation to be valid up to the fan and after the fan, but you can't apply Bernoulli's across the fan because we're adding work input. So that's the point made in point 5, I think, on the previous slide. And in C here, they make the point that if you add heat, so here they've got some burning logs, you can't can't really apply Bernoulli's equation across a fire like that. It would be applicable before the heat is added and after the heat is added, but you can't apply it across because you're adding energy to the flow. They also make the same point that you can't apply it near the wall because you would have these viscous boundary layers. Again, they're shown greatly enlarged here, but you get the idea. So now you know something about the limitations of Bernoulli's equation. So let's apply Bernoulli's equation to a simple example. This is a very simple example. I'm going to do some more complex examples in subsequent videos. And we're going to talk a lot about the application of Bernoulli's equation to the measurement of flow. And you'll see that in the lab as well. So the example here is water at 20 degrees C in a large diameter tank discharges through a small pipe. And you can see the pipe in the side of the tank here. The height of the tank is 5.2 meters. The discharge pipe is located 1.3 meters from the bottom of the tank. The discharge pipe has an inside diameter of 2.5 centimeters. I've drawn it here. And the tank drains slowly such that the flow can be approximated as steady and frictionless. So we can use Bernoulli's equation. And the problem is to calculate the flow rate, the discharge flow rate from the tank in liters per second. Okay, you always start any Bernoulli analysis by drawing a hypothetical streamline. It doesn't have to be perfect, but for example, I could imagine a particle of fluid being drawn down from the surface and then eventually discharging from the nozzle. So start by drawing a streamline. That's important. So point 1 here is at the free surface, and point 2 is at the discharge from the pipe, right at the very discharge. Now, point 1 and 2 are somewhat arbitrary. You can use other points. We'll talk about this in future examples. So other points are possible, but as you'll see, this is a pretty smart choice that makes the analysis easy. So now we're going to apply Bernoulli's equation between points 1 and 2. So we've got the kinetic energy at 1, the pressure energy at 1, the potential energy at 1, all per unit mass, of course, equals the kinetic energy at 2, the pressure energy at 2, and the potential energy at 2, all per unit mass. So let's start evaluating some of these terms. So you can recall from a previous discussion, I think it was the previous video, that where a flow discharges to atmosphere, so at point 2 here, where the flow discharges to atmosphere, it's reasonable to assume that the pressure at that point is equal to atmospheric pressure. Unless the fluid is supersonic, there are some other caveats, but for most engineering applications, it's perfectly acceptable to assume that the pressure at 2 is equal to atmospheric pressure. And of course, the pressure at 1 up here is also equal to atmospheric pressure. Now, of course, there's a slight change in pressure from 1 to 2 in the air, but we're going to neglect that. Remember back to chapter 2, the density of air is 1,000 times less than the density of water, so we assume that atmospheric pressure doesn't change significantly over this distance, which is a matter of a couple of meters. So P1 equals P2 equals atmospheric pressure. So they appear on opposite sides of the equation. We can cancel them out. If this was a sealed tank and we knew the pressure at the top of the tank in this space up here, and of course that's what we would enter for P1. So we can it's very easy to handle sealed tanks as well. But in this case, the tank is open, so the pressure at 1 and the pressure at 2 are the same. We can cancel them. So in the next slide, I think I've rewritten this with those two terms eliminated. So now we just have the kinetic energy per unit mass plus the potential energy per unit mass at 1 equals the kinetic energy at 2 per unit mass plus the kinetic energy plus the potential energy at 2 per unit mass. Now you're told in the problem that the diameter of the tank is large. So this diameter here is large, and the reason you're told that is so that you can come to the conclusion that the level of the tank drops very slowly. So the velocity here, V1, is going to be small. If you were told the diameter of the tank, you could actually calculate the velocity at 1. But since you're not given it and you're told it's large, we're going to make the assumption that the velocity at 1 is 0. So we can neglect the kinetic energy at 0.1. That's a reasonable assumption. Now notice here I'm measuring the elevation Z from the bottom of the tank. You can pick any convenient datum or reference line that you want. So if we pick the bottom of the tank as the datum, we have Z1 equals 5.2 meters, the height of the tank, and Z2, the discharge point, is 1.3 meters. And so now we've got Z1 and Z2. We can solve for V2. And that's what I've done here. I've solved for V2. It equals 2G Z1 minus Z2. And I've made the substitution, 2 times 9.81, and the difference in the elevation, 5.2 minus 1.3 meters. And you can see the units balance. We have meters squared per second squared, square rooted, gives you 8.75 meters per second. You may notice that this velocity equals, 2g delta h is the same as for a free-falling object. In your physics course, your dynamics course, you've probably done these kinds of calculations. And so this is the fluid dynamics equivalent of a falling object. All of the potential energy at 1 has been converted to kinetic energy at 2. Remember, we have no losses, so it's just like a falling object. There's no viscous losses in Bernoulli's equation. So now we have the velocity at 2. We just got to multiply the velocity at 2 times the area at 2, pi d2 squared upon 4. The inside diameter of that pipe is 2.5 centimeters. So pi times 0.025 meters squared. Of course, we're making the assumption here of one-dimensional flow. And that gives 0.00429 cubic meters per second. And then I've used the fact that there's 1,000 liters in a cubic meter to convert that to 4.29 liters per second. So that's a fairly low discharge rate. For a large tank, it's reasonable that the surface level here would fall slowly. If you were given the diameter of the tank, you could correct for that effect, but you're not in this case. So I'm just going to end by asking, will the actual flow, if you were to set up a tank with water with exactly these dimensions in a large tank, will the actual flow be higher or lower? And why? You might want to pause the video and just think about this for a moment. The answer, of course, is that in all likelihood, you'd get a slightly lower flow. The reason is you've neglected viscosity. Water has some viscosity. It's fairly low, but it has some viscosity. You actually have, a velocity profile across here, and it sticks at the surface. So there's some drag. This pipe would exert some drag on the flow because of the no-slip condition. So you're going to get a slightly lower velocity. Also, there'd be these sharp edges here, and we'll learn about that later on. These sharp edge inlets cause some turbulence, and that burns up some energy because of mixing. It dissipates some energy. And so Bernoulli's equation assumes there's no energy loss from 1 to 2, but in reality, there is some energy loss due to fluid friction. And so you'd probably get a value just slightly lower than this. But nevertheless, it's a very good engineering approximation for most flows. Now, this is a very simple example. I'm going to do some more complicated examples in subsequent videos.